Okay, let's kind of think about sort of a weird question, but let's see what kind of your intuition is. So let's take a set, a subset of the natural of 1 up to n uniformly at random. Or in other words, you can think of like you flip n coins, like for each element of 1 up to n, flip a coin. If it's heads, you put it in S. If it's tails, you don't put it in S, right? I know this is not really a probability course, but yeah, you'll see why this is relevant. So, so I'm going to define 2 events. So let E be the event that S doesn't have a solution, so doesn't contain, let's say, some X, Y, Z, such that I'm going to write an arbitrary, very strange looking equation. Just pick any equation you want. So let's say x cubed plus 4y equals z to the 5 minus 20. Okay, I'm just writing down random. And now let F be the event that S does not contain any numbers which are a valid Canadian phone number. Okay, so it's just a completely arbitrary condition, right? So it doesn't contain any valid Canadian phone numbers. So 2 quite strange conditions. Now, suppose we generate this set, but you can't see it, right? It's under a blanket or something. I look and I say, I tell you, so each of these things has some likelihood, right? So I look under the thing and I can see this set. I can say, I tell you, you know what? Event E holds for this set. So when I've given you that information, do you think it makes event F become more likely to hold or less likely to hold? Or the same? Yeah, I guess, yeah, so I guess if n was small, then you wouldn't have any of those. Yeah, so let's say n is very. So basically, if you take any of the things in S and you phone them, it says it can't connect. So yeah, if I peek at the set and I check whether E is satisfied, and now I ask now you update your probability of whether you think F is satisfied, and will that go up or down? Maybe let's do a vote, like thumbs up or thumbs down. You also included people online too. So you think it's the probability of E or F occurring goes up or goes down? I mean, or stays the same, or it's kind of independent or something. In some sense, I tried to write things that are completely weird and arbitrary here because I don't really care what these properties are in some sense. I just care about a certain property of them, but. Yeah, actually, so E is that doesn't have these solutions, but anyway. The same thing works in the reverse order, like kind of, if E happens and it doesn't have one of these solutions, then it should correlate with the S being kind of small, right?
Mhm.
Yeah, in case people didn't hear that online, so, yeah, if you take a uniformly random set, the probability, like if the event that E happens will be less likely if S is big. Because you're more likely to start seeing solutions to these things. And the same thing, if S is big, you're more likely to start seeing some phone numbers in your set. And sort of E happening, so E happening is kind of correlated with S being small. And F happening is correlated with S being small. So maybe they're kind of correlated with each other. So maybe if E happens, F is more likely to happen. And that's actually the kind of philosophy that I wanted to kind of come to with this. So actually, we're going to see that if E happens, then F is actually more likely to happen, or at least as likely. So this relates to something called the Harris-Kleitman inequality. So let me first give a definition. If I take a subset of our set of 1 up to n, we say it's downward closed. If, or we just say is a down set. It's kind of faster to write than downward closed. If for all, like basically if it's closed under taking subsets. So if I take a set in F, and I take a subset of it, then it's still in F. Then E is in F for all B is subset. And then kind of analogously, you've got upward closed or an upset. So if A being an F and B being a superset of A implies that B is an F. Kind of awkward terminology, saying upset, because like that actually has a meaning in English, right? Being upset, but this is an upset, not upset. What we're going to prove something which this is a thing that goes by many different names. If you're a probabilist, you probably call it Harris's inequality or something. Combinatorics, people might call it Kleitman's inequality. Probably has other names as well. So I'm just gonna like say both people are right and just say it's the Harris-Kleitman inequality. Says, let's say F, if F and G are down sets, power set of 1 up to n, then. So what I'm going to do is I should think of F and G as sort of being like events, right? Like, here we had the event that a set S doesn't contain a solution to some crazy equation. You could just say, take script, curly F to be the collection of all sets that don't have a solution to that. That's closed under taking subsets, right? You don't have a solution to some crazy equation, then no subset also, has a solution, right? You don't have any Canadian phone numbers, then no subset has a Canadian phone number, right? So what this is kind of saying is looking at the collection of all sets that satisfy both conditions. I'm going to divide by 2 to the n, which makes it into like a probability, right? This is like the things satisfying both divided by all the subsets. And that's got to be at least probability of F over 2 to the n. Or sorry, the size of F over 2 to the n times the size of G over 2 to the n. So like kind of in a probability kind of terminology, like, if E and F are sort of downward closed events, kind of. By this, I just mean, like, if one of them happens, then if you replace the set with a subset, then the event still happens. Then you get that the probability that both of them happen is at least the probability that the first one happens. That's the probability that the second one happens. So if these were independent, you'd have equality, right? But this is saying if they're downward closed, you've got at least like what you would have if they're independent, right? So this tells you that if I told you event E happens in that example, then okay, if they were independent, maybe the probability that F happens stays the same, but it can't go down. So if I tell you E happens, then the probability F occurs as well goes up. So to anyone who got their thumbs up, then that was the right answer. Anyone who had the thumb sideways? That could be the answer too if they're independent. I can't tell if these things are independent or not, right? But can you see how this is kind of like the probability of kind of 2 events happening at the same time, probability of the first event, the second event, right? By the way, this is like I mean, the reason why probability people are interested in this, right, is this is a very useful statement of probability. Often, like I think this may came from like percolation theory. So imagine you have a grid and you include each edge with probability P or something, and you want to know, does this have a big infinite component or something? Like you might want to understand probabilities of like intersections of, you want to understand like the probability 2 different events happen, but those events aren't independent. Like maybe you want to know the probability there's a path from here to here, and probability there's a path from here to here or something. Well, those paths may kind of touch each other and intersect, so those are not independent events. But if they're both like downward closed or upward closed or whatever, so this also works for upsets, right? Because if you make them both downsets or both upsets, they both work. Yeah, then you can at least estimate the probability by just taking the product of the 2 events. And it simplifies your life. Any questions about this statement or anything related to it? No. There's also various strengthenings of this, like that you may have heard of the FKG inequality. There's something called the 4 functions theorem. But This one is particularly relevant for this class. Okay, so let's do it by induction on N. Okay, for N equals 1, you can just check. I mean, there aren't very many downsets for N equals 1. So you could, I mean, can check kind of all possibilities. And I'll just say that the inequality is true in this case. I guess we could have maybe done N equals 0, and that's even more trivial, but anyway. Now, let's say N is at least 2. Okay, so what we're gonna do is something kind of similar to some stuff we did in both of the last 2 lectures. Like, one key idea was to look at you have a set system, take all the sets that contain a certain point, and then take all the sets that don't contain that point. You kind of break your family up, apply induction on both of them, and put things back together. So that's actually what we're going to do here. So let's let F minus be the set of all things in F, such that N is not in that set. So basically, this is now like a family of sets that lives in like the power set of N minus 1, right? Taking all the things that don't have the element N. Then we're going to look at things that do have the element N. But I want to treat this also like a subset of our set of 1 up to N minus 1. But it has N in it, so that's kind of a problem. And I also want it to be a downset, but downsets have to have the empty set in them. But I could just take all the things that have N, all the sets that have N in them, and just take N away, right? And that's gonna be a natural choice. So it's all the sets A minus N, such that A is in F and N is in N. And this is also living in 2 to the N minus 1. Right, so to imply induction, I need both of these to be downsets. That's going to work, right? Because if I have something, for example, a set in F minus, well, in particular, that's a set in F. And so all of its subsets are in F. But all of its subsets also don't have the element N. So all of its subsets are in F minus, right? Similar here, if I take a set in F plus, well, that was a set in F that had N. But yeah, so if I take a subset of this, that subset with N is in F. But so then that subset without N is in F plus, because I would just take it away, right? So F minus and F plus are downsets. Okay, so. Here's a question. You think about F minus and F plus, which one's bigger? Yeah, maybe they might have the same size, but which one is not smaller? So, a thumbs up if you think F plus is smaller, thumbs down if you think F minus is smaller. Actually, remember this intuition, right? A down set correlates with small sets. Right, so a down set kind of typically has smaller sets, right? Yeah, anyway, F minus is big, right? Because basically for anything that's in here, like in fact, F plus is a subset of F minus. If I've got a set in here, then it came from something in F that had n in it, but all the subsets of that are in F. I can just take out n, and I get a set here. But actually, that's the same set as this. Yeah. So the F minus is bigger. So like what I'm trying to say here is F plus is actually a subset of F minus. Because if I take set in F with n being an element of A, then A minus n is in F, but that implies it's actually in F minus. So now let's also define. So you can also, so we're supposed to have two families, F and G, right? I've been focusing all my attention on F so far, but we can just do the same thing for G, right? So G minus, we can define G minus and G plus. Analogously, G minus is the things in G without n. This is the thing with n, and then you delete n from it. Okay. Let's do some algebra now. So and look at this quantity 2 to the n times F intersect G, which is just what you get. I'm getting rid of the fractions here. So imagine you just multiply everything here by 4 to the n, right? You're going to get rid of these 2 to the n, 2 to the n, and then you're going to have an extra 2 to the n here. I'm just getting rid of these fractions, and I want to show. So I want to show 2 to the n times this is at least this times this. That makes sense. Okay? So I can I guess a key thing is here I can express this intersection in terms of F minus, F plus, G minus, and G plus. Because if you have a common element of G and G, or F and G, either it's an F minus and G minus, because like it's a set that doesn't include n, or it like, yeah, it's a set in well, it does include n, and then there's a corresponding set in F plus and G plus. So what I'm trying to say here is that this is 2 to the n F minus intersect G minus plus F plus intersect G plus. Because again, a common element of these two things either doesn't include n or does include n, and those are kind of counted by these two things. So by induction, so keep my 2 to the n. Okay, we have to like do some thinking about where these all these different 2 to the n's. So when n is equal to n minus 1, right? All these 2 to the n's become 2 to the n minus 1s. So okay, that's what we want. I think this is like f minus g minus over 2 to the n minus 1. So that, yeah, I think normally we have like this over 2 to the n minus 1 is at least, yeah, this with 2 to the n minus 1s on the bottom. Like you apply the statement here with a bunch of 2 to the n minus 1s everywhere, but just move one over there. I think that gives the right bound. That makes sense. Just arithmetic. Which is so equal to 2 times f minus g minus plus f plus e plus. Well, it's kind of hopeless, right? Because in the end, what I want to get is size of f, size of g. But like, I mean, this is kind of related to that, but it's missing all those cross terms and stuff. Like, we want to have f minus times g minus f minus times g plus, and but anyway, it's do some kind of clever algebra. You find out this is what you wanted, almost. So what I would want it to be is this, because that's the size of f and the size of g. It's this plus f plus minus f minus 10 times g plus minus g minus. If you did all the arithmetic, you'd see that this actually does, like the cross terms cancel basically. Remember where we started, where we want to get to is this being at least size of f and size of g. If this is equal to size of f, that's equal to the size of g. And then this thing, I guess we want to be negative or non-positive. But it is, actually. Because remember, f minus is bigger than f plus, right? Oh, yeah, f is some collection. F lives in, it's a subset of 2 to the n. So F is downward closed, so if I have something in,
Right, yes.
I can always just pluck out an element and it'll still be.
Right, right.
So in case people couldn't hear that online, like the question was, how do we know that if a set is in F and N is in that, F is in the set, how do we know this? And this is because of the downset condition. Yeah, that's a subset of A. Exactly. Right, so if we kind of go back and we see that, oh yeah, F minus is supposed to be bigger than F plus and same with G minus and G plus, and then analogously, then this is like non-positive, non-positive, so yeah, you get this inequality. This part is less than or equal to 0. Yeah. That's right, great, yeah. Right. Looks like it's going the other way, right?
No.
This is correct, okay, yeah, fine, okay. Yeah, okay. So yeah, that's how that works. Any other questions about this proof? Yeah, we're gonna kind of focus on using this in various kind of extremal combinatorics applications, but like I said, it's also super important in probability theory. So now with the last kind of 15 minutes or something, I'm gonna get us kind of prepared for the next lecture because it's a little bit maybe longer of a topic. So here's the basic problem. So what is the minimum M such that there exists coloring of the set N choose K with M colors such that any two sets the same color have non-empty intersection. It's kind of coming all the way back to the first lecture, kind of, right? Erich Corrado was looking for the biggest collection with this non-empty intersection, like biggest intersecting family in here. Right? Now what we're trying to do is actually partition into intersecting families. And we want to do that as efficiently as possible. I mean, so we again have one trivial case, right? If K is bigger than N over 2, then use just one color, right? So because by pigeonhole, any two sets intersect, right? Yeah, we're kind of interested in the non-trivial case. Yeah, any kind of I don't know, I mean, thoughts about a lower bound on M or upper bound, like a construction or a. I guess anything that comes to mind. Yeah, because once you take sets that don't contain one, now they're all forced into this small thing and then you got pigeonholed again, right? So yeah, that's gonna work. So. Yeah, so in a case like K is M2. Two colors. Works. Right, so color one. We can think of it as colors, or we can think of it as two intersecting families, right? So my first second family will be set of all A. Size K. What's that? One is an A. And then yeah, F2 is everything else. Yeah, I guess that completely answers the question in that case, because you can't do one color, right? So. Any thought about how to generalize that? This is the right idea, actually. Any thoughts from people online as well? Yeah, the idea here was like, once you've ripped off the number one from everything, everything's got to intersect now, because you're in a ground set that's too small. Actually, the kind of key idea here is you should just do this, like you should just take everything that contains one, everything that contains two that doesn't contain one, everything that contains three that doesn't contain one or two. So basically everything with the minimum element is I. Keep doing that. And now all of the sets left over are shrunk into a smaller and smaller ground set until they can't be disjoint and then stop, and that's your last color. So an example is so let's say let Fi be the set of all sets size K in 1 up to N, such that I is the minimum element of A. And you have to think about how the math works. Like you want to keep going until your ground set has size 2K minus 1. Right? That's when everything has to intersect, right? So you take F1, 2, up to F n minus 2K plus 1. And another set, which is, let's say, I'll call it F n minus 2K plus 2, which is everything left over. So therefore, there is a construction using n minus 2K plus 2 sets for colors. But that's just like an upper bound, right? On the number of colors. It doesn't really, it doesn't answer the question completely. For a lower bound, does anyone have any idea of anything, okay, a lower bound bigger than like, let's say. A lower bound that depends on n and k, so don't give me 0 or something negative one. Like, what's a non-trivial lower bound on this quantity, this number of colors? Like anything you can think of. Yeah, yeah, certainly each of your colors can't be bigger than n-1 choose k-1, right? You can't even have yeah, no single color can be bigger than that, so. The lower bound. So, no color. Can appear. More than. n-1 choose k-1 times. By Harris-Kleitman. So yeah, so definitely M is going to be at least n choose k over n-1 choose k-1, which if you plug in the factorials and cancel stuff, gives you n over k. Yeah, I would call that a non-trivial lower bound. But it's still pretty far, right? Like, if you think of k as fixed and n goes to infinity, like this is just basically n, right? If k is 10 or something, right? This is like n minus 18 or something, whereas this one would be n over 10. So there's quite a gap between these two things, but at least, yeah, it should grow linearly with n. Somewhere between n over k and n minus 2k plus 2. So what we're going to prove next time is that this is the answer. So it is really that. This is actually like it was an old problem known as Kneeser's conjecture in 1955, which said basically you can't do better than n minus 2k plus 2 colors. This was proved by Lobaz, 78. Surprising thing about this proof is that it uses topology. Something maybe you don't expect in a combinatorics problem like this. So yeah, we'll give this proof next time. Doesn't like you don't have to worry if you don't know about topology really. Like you don't have to go and read a book on topology before next class. It's really based on quite simple kind of principles, but they are kind of topological. So here's the kind of idea that it's based on. So okay, we'll take a circle. So I mean S1, like it's a set of points at distance 1 from the origin, right? Color with 2 colors. color with two colors. Such that both color classes. No, sorry, just one color class. So two colors, red and blue. Such that the red points form open set or a closed set. I guess in some sense, okay, in this one-dimensional case, that's also going to mean that the complement, the blue set's also open or closed. When we go to higher dimensions, we're gonna have a bunch of sets that are open or closed, and the last one doesn't have to be, but anyway. So then there exists antipodal points of the same color. Basically, we're going to use a generalization of this to coloring the points of the sphere in higher dimensions. But yeah. Like this is almost false, right? In some sense, like what I would do if I was trying to not have it, I want to color in two colors to not have antipodal points that are the same color. I guess, I mean, I would do something like this. I'd pick something here and put like an open interval, but you know, at the antipodal point, I would put it closed. I'd color all of this red, right? And I'd color this blue. But what I just did was kind of illegal, right? Because the red points, it's like open on one side, closed on the other side. But I wasn't allowed to do that. I have to make it open on both sides or closed on both. Like, so now you're gonna have antipodal points in one of the colors. It's just gonna happen. You can now try to do another strategy, but this is saying no matter how you do it, you're always gonna have these antipodal points of the same color. Somehow that's gonna correspond to not being able to color using intersecting boundaries with a small number of colors. Not clear how that's gonna work, but we'll see next time. Any questions or anything? Yeah. So that I just mean points that are exactly opposite on the circle. Yeah, so there's a line through them going through the origin. That's a good question. All these things like about things that are not, I mean, yeah, feel free to ask these questions. Yeah. Any other questions? See you guys on Friday.